This video lesson, as it pertains to harmonic motion, culminates with behaviors that we see in waves. So looking at waves, right, and the way they can behave, right, a primary thing that they do is interfere with one another. When you send waves, right, you can send them as single pulses, so you can send just one quick burst, one quick wave is going to move, right, and it's going to go through whatever medium it is, hit a boundary, and it can reflect, it can go through that boundary. But if you get two or more waves that interfere with one another, right, that interact, right, we're always going to treat that interaction between waves as an interference. Sometimes those waves will add together, sometimes they'll subtract from one another, right? But ultimately, when they pass through, which means they get to the same location at the same time, they interfere, right? This can cause an increase in amplitude, this can cause a decrease in amplitude. This idea of the principle of superposition basically says that you're going to get two waves that are moving. They can be moving in the same direction, they can be moving in opposite directions, but as soon as they interfere with one another, that means they're located in the same spot at the same time, thus they are in superposition, right? Same spot, same time. So what happens is we get two or more waves that appear to look like one single wave for a very brief moment of time, and that moment of time is when they are at the same location, right? And then what happens depends on the amplitude and then the phase of the interfering waves, right? So the phase could be a crest interfering with a crest, a trough interfering with a trough, or crest with a trough. So as we look at the animation to the right, which is going to show us constructive interference, we see a wave coming from the left and a wave coming from the right. So these two waves collide with one another, and at the same time, when they get to the same location, we see the two crests amplify each other, right? So when we get constructive interference, we see an amplify, or we see the actual amplitudes increase in magnitude. So let's say the initial wave from the left, so let's say this wave, we'll let it run back to the beginning here. Let's say a wave on the left has an amplitude of 3 meters, and the wave on the right has an amplitude of 5 meters. When they are in the same location, which would be right there, we would add those amplitudes together to get a total amplitude of 5 meters, right? So that single wave that would occur in that one location would be 5 meters tall. Then those waves will continue propagating as they were, right? They're going to separate, and we're going to see the 2 and 3 meters continue moving as they were. So we only see this constructive interference when they're in the same spot at the same time. And they have to be in phase with one another, right? So constructive interference will occur when they're in phase. We're going to see destructive interference when they're out of phase. So in phase means two crests hit or two troughs are interacting with one another. Common example of this, right? Think about water sports, right? If you're tubing and you're playing a good old game of battle tubes, and you get a driver that's able to whip around and make all sorts of waves, when those waves crash and hit together, if you get the crest and the crest, you get the big wave to hit, or if you get a trough and a trough in the water, it actually makes a bigger well that you can fall into, right? So we see this quite a bit with water. Now, destructive interference is our next type of wave behavior. And this occurs when we get two waves that are out of phase. So you get a crest that interferes with a trough. And what we see, right, so I'm going to pause this animation real quick. So the top wave does not move. The middle wave is moving. The bottom wave, which is the thicker of the three waves, that is the sum of the wave interaction, right? So when they become superimposed on each other, right, that is what we get as a result. So as this middle wave continues to move, right here, we're going to see that everything is in phase, right? So we see the crests are lined up, the troughs are lined up, so we see constructive interference. The amplitude on the bottom wave would be the sum of the amplitudes of the two waves above it. As that middle wave continues to move, right, now we get more and more out of phase. So here, we see that we're out of phase. So our net wave, our resultant wave, is smaller. This wave continues to move, and eventually we get as perfectly out of phase as the simulation will let us get. And we see the resultant wave is 0 or very close to 0 in this simulation because we have a trough lined up with a crest, we have a trough lined up with a crest, right? So everything about these two waves is perfectly out of phase, thus the amplitude shrinks. So through destructive interference, we get waves to shrink, right? Thus we get the resultant wave at that point in time to be smaller, right? The amplitude goes down. When we are in phase, so we get constructive interference, we get an increase in the overall amplitude that we see. And if we let this just play out here, right, you can see that resultant wave in the bottom changing based on the two waves above being in phase, out of phase, and some combination of those. Now, as these waves transmit and reflect, right? So here we're going to see other behaviors, right? We're going to see reflection, and then what happens when these waves reflect. So we take from one medium to another, right? It's going to interact with a boundary. Because if you get a wave to just travel through a consistent medium, you're not going to get reflection, you're not going to get transmission. It has to be at a boundary, right? So when the wave interacts with a boundary from one medium to another, that's how we're going to see how this wave is going to reflect or how that wave could transmit through. Right? So as we look here, right, waves can be reflected, transmitted, or both, right, depending on what happens. So in the bottom left, right, this would be a fixed boundary, right? So a fixed boundary means that when this wave makes contact, that boundary is not going to move. So we see a single wave pulse come in from the left, and it is going to hit that fixed boundary, and that fixed boundary is going to have a higher density. And because it has a higher density, we're going to see this wave press into that boundary, and as it does so, it can't cause that boundary to move, so the wave inverts and reflects out of phase. So if we send in a crest like we do here, we're going to see a trough leave. If we send in a trough, it is going to hit and it is going to reflect out of phase. Right? Whenever we hit a fixed boundary, we're going to see the wave flip. Right? Send in a crest, get a trough, send a trough, get a crest. All the time. Right? That's what's going to happen when we hit that higher density fixed boundary. That wave will reflect out of phase. Now, when we look at a lower density or a free boundary, right? So note the circle here is not filled in, so this would be a free boundary. Same deal. We're going to send in a pulse from left to right. This wave pulse will now hit the lower density free boundary, and now that boundary will move based on it having a lower density. So we're going to see that boundary move, and the reflected wave is going to be in phase with the incident wave. And those are some terms to get used to. The incident wave is what we send. The incident wave is what is generated. The reflected wave is what comes back. So here we get an incident wave that is a crest, hits a lower density free boundary, and it reflects as a crest as well. Going back to the fixed boundary, we have a crest sent as an incident wave. We have a reflected wave as a trough. All right, so again, it depends on that density. So if you go from higher density to lower density, the reflection is going to be in phase. If you go from low to high density, the reflection will be out of phase. And how those reflections and transmissions, or the incident waves versus the reflected waves, how they interact with one another will form a standing wave under the right set of circumstances. So what we see here, an incident wave in blue and the reflected wave in red. And what they generate is the standing wave that is in black. When you get the right combination of incident wave with reflected wave, you're able to generate a standing wave. A couple points to note on these standing waves. The dots in red, those are called nodes. And if you watch the nodes the entire time, regardless of how in phase or out of phase the incident and reflected waves are, those nodes do not move, right? They don't move. They stay put regardless of whether it is perfectly in phase, perfectly out of phase, or some degree of being out of phase that's not maxed out. Then we have the antinodes. And if you notice the antinodes, those are the local maximum or minimum, right? So what we see is we see a crest or a trough. The antinode is located on the crest and on the trough at the apex, right? At that highest point. Sometimes those will be at 0. Sometimes they'll be maxed out. And as we see, right, through this simulation, so if I pause it, when we are perfectly out of phase, there is no wave pattern, right? The wave pattern for that moment is gone. As we get more in phase, right, so here we are perfectly in phase, we see constructive interference. So ultimately, these standing waves are generated based on constructive and destructive interference of an incident and a reflected wave. And they get the term standing wave because they have points along them, which are the nodes, that don't appear to be moving, right? And they don't move. Those particles, right, whether it's a string or a spring or whether it's water particles, at the nodes, they don't move. They don't move at all. They don't move anywhere. That's why we get the standing wave, as it's called, because it appears to be moving in place instead of actually going somewhere. Now, with this being paused, it's a good time to ask, how many wavelengths are in this standing wave? Remember to count your wavelengths. It's a full crest and a full trough. So here we've got a crest with a trough. There's one wave, crest with a trough. We have 2 waves, right? So we have 2 wavelengths here. If you also want to consider, right, we go crest to crest and trough to trough, right? There we would have a wave and we would have another wave, right? So we have 2 full wave patterns that are present. Now, in order to generate a standing wave pattern, right, what we see in the simulation to the right are a lot of different standing wave possibilities based on frequencies, based on fixed ends, and based on free ends, right? You need to have 2 or more waves that are at the same frequency and the same amplitude, right? That you need to have that in order for the standing wave to actually be generated. If you get different amplitude waves, it's not going to work out in a nice, neat fashion. You get some weird, odd, goofy looking wave that's not continuous and it's very chaotic looking. So they need to have the same frequency and the same amplitude. If one of those is off, you don't produce a standing wave. You produce a chaotic looking wave. They have to be traveling different directions, which means you have an incident wave that is interfering with a reflected wave. And typically, right, and again, right, we're going to see that reflected wave. So if you look at this at this simulation, right, the black on each of those posts is representing a fixed end. The little hoop is representing a free end. So as you work across, right, we see the incident wave and the reflected wave and how those patterns are able to generate these standing waves. And you can point out where the nodes are and where the antinodes are based on a fixed location and a moving location pending frequencies. And based on wave speed, each of these waves, if you go across the row of 4, they're all moving at the same speed. They don't necessarily look like it, but they are. Because remember, wave speed is based on frequency of the wave and wavelength. So on the far left-hand side, those 3 in the left-hand column, those have by far the longest wavelength, but they have a much lower frequency. The ones in the far right, which appear to be moving faster, are not. They have a higher frequency, which is then associated with a shorter wavelength. So as you work across the rows, all of those are moving at the same speed. They just each have a different frequency and a different wavelength. And based on the frequency and the amplitudes, we're able to produce standing waves from the incident and the reflected waves. So there we see our wave behaviors, our wave patterns, and production of a standing wave. And it all ties back into the idea of harmonic oscillation, because these waves, if you notice, are obeying one set pattern over and over and over again. They're doing a repeating, very predictable motion, which ultimately is a harmonic oscillator.